So the scalar control of AC drives gives a good operating performance but poor dynamic response due to the deviation of the air flux linkage from the set values. Air flux, that is the flux set up in the air gap, that is between the stator and the rotor. The variation occurs in both magnitude as well as the phase. So basically in case of the scalar control, both torque and the flux. Here flux is nothing but the speed. So we can use the another alternative word as a thus in a scalar control, both torque and the speed are the functions of voltage or the current and the frequency, which are mostly interdependent on each other, giving a very sluggish operation of a drive. It means that there is a dependent behavior in between the flux and the torque. As you will try to control the speed, a torque will get automatically changed, and if you wish to control the torque, the speed will get automatically changed. So we can say that there is not a decoupling in between the torque and the speed, means torque and the flux. So such kind of the speed control or the torque control is not suitable where there is a very dynamic change in the load pattern. So obviously in such a way, such a motor control will give you the sluggish response. So this variation basically gives a sluggish response in case of the torque as well as the speed. So in case of the most suitable, the most suitable is obviously vector control, because in case of the vector control, there is a field oriented control. It gives more accurate control of AC motors as compared to the scalar control. So they are used in a drive applications where oscillations in air gap flux linkage are intolerable. That is in case of the robotic applications, centrifuges, servos, etc. So here it is a vector control technique, allows a squirrel cage induction motor to be driven with a high dynamic performance that is comparable to the characteristics of the DC machine, that is DC separately excited motor. So the concept of vector control has been arised, or we can say it is very analogous to the separately excited DC motor. As in case of the induction motor, stator current and rotor current both are coupled so that there is no independent variation, but not a same case in case of the DC separately excited motor. So here we are using the sentence that in case of the induction motor, stator current and rotor current both are coupled. It means that if I wish to change the magnitude of the stator current, there is a change in the rotor current. It is due to the slip present in between the air gap, obviously in the induction motor. And if I wish to change the rotor current, there is a certain change in the stator current. So it means that the torque and the speed, means torque and the flux, both are coupled to each other. One will give the variation in the another and vice versa. So how that induction motor, vector control of an induction motor is very analogous to the DC separate excited motor. Let us see. Here a simple single line circuit diagram has been drawn for the better understanding of the DC separately excited motor circuit diagram. So armature is fed from the DC input source, it's a armature voltage. Field circuit is fed from the another a separate DC source that is required for the excitation. So as we knew that the torque in case of the DC machine, DC motor is directly proportional to flux and armature current. Here that proportionality constant is replaced by the K. So torque is equal to K into phi Ia. Here the phi is nothing but the flux set up in this field circuit, which is obviously depends on a separate DC source connected across the field circuit terminal, field winding terminal. So we can use phi by If, that is field current, and Ia as it is. So in case of the DC separately excited motor, the armature current and the field current both are 90 degree to each other. So it is a sine of 90. The angle between these two is a sine of 90, and sine of 90 is equal to 1. So we have not written the sine of 90. But see that 90-degree angle is between the field current and the armature current. And this field current is nothing but a direct axis current, and armature current is nothing but the quadrature axis current. See, as field current IF is direct axis component and armature current IA is a quadrature axis component. Here, if you wish to change the torque, you need to change either of the field current or either of the armature current. Basically, in case of the DC separately excited motor, the torque is directly proportional to the armature current, but while keeping this field current as a constant. And obviously we can keep it as a constant by keeping the constant magnitude of the separately excited field winding. So torque is directly proportional to armature current provided that field current is a constant, whereas speed is directly proportional to the 1 upon phi, means speed is inversely proportional to the flux. So, and the flux is nothing but depends on the excitation value, that is the field current. So by keeping the armature circuit current constant, if I vary the field current, speed will get vary. So it means that there is a decoupling in between the armature current and the field current, nothing but the torque and obviously a flux, torque and a speed. So such kind of the behavior is required to imply in case of the three-phase induction motor. So that is the concept of vector control in induction motor drives. So what is vector control? So vector control gives a decoupling control or the separate control over the torque and the speed in case of the three-phase induction motor. So it is possible to get a DC machine like performance from an induction motor if the machine control is done by using a synchronously rotating reference frame, where sinusoidal variable appears as a steady state DC quantities.